and welcome to this video on intercepts for rational functions. Okay, there's two pieces of this that you need to be aware of before you go into this video. One is that you have a decent understanding of how intercepts work. I'll do a quick overview and review of that using a sketchpad demo. The second is that you've seen rational functions before, and they're functions that look like this. Okay, you should have had a working definition of them, toyed with them a little bit in class, and now we're going to drill down and find something very specific in them, which is their intercepts. Okay, before we go there, I will take a quick review of intercepts. So a y-intercept, okay, on a function is very simply just a point that the function crosses the y-axis. Okay, and you should be pretty well trained in this point as you hear the idea of y-intercept to say x equals 0. Okay? If you're not, I'll show you that in the demo I'm going to do quickly. X-intercepts, or intercept, you need to notice there could be more than one of them. Okay? Could be one, could be more than one. They are points that a function goes through on the x-axis. And we need you to be decently well trained when you hear x-intercepts to think y equals 0. Okay? So, real quickly, if you're not sure where that comes from, it's just a memorized fact, you should always have some reflection on it. And I'll take you over here to see that. Okay? So, if you look at a point on the y-axis, no matter where I slide it, if you notice, okay, it will always have an x value of 0, no matter where I put it. Similarly, for a point on the x-axis, no matter where I put it, it will have a y value of 0. So this is applicable, you'll notice, to linear functions, but also if I actually were to add additional roots to the function, where now that's got two x-intercepts, or two zeros, you can see there are 2 points whose y values are zeros. And again, no matter where I move the x-intercepts, the y value is always 0. No matter where I use the y-intercept, its x value over here is always going to be 0. And it doesn't matter what type of function you're dealing with. If you were to deal with a cubic function who's got up to 3 x-intercepts that this example does, you would see 3 points whose x values vary, but their y values are 0. And again, its y-intercept has an x value of 0, no matter where I put it. Okay? So, that is where this idea comes from in terms of we want you to be able to say y-intercept implies that x is 0, and x-intercept implies that y is 0. Okay? So, moving right along to how this is going to be applied to rational functions, let's take a look. Well, if we want to be able to sit there and say the x-intercept means y equals 0, and the y-intercept implies that x equals 0, you'll be setting those values to 0 as you're dealing with the functions. Okay? So, one of the things that you'll notice if you look at the examples here, they look like big ugly fractions with variables in them. That's a layman's kind of terms for what rational functions are. Again, you should have a better definition from class. But if you notice here, it's like a big ugly fraction, but it's still a fraction. And you have to remember something about fractions from like 3rd grade. If you have a fraction like a over b, and it's equal to 0, there's only one way that can happen, and that's for the numerator to be 0. So here, if you have a over b equals 0, it means a is 0. Okay? Don't forget there's no such thing as dividing by 0, so you might just kind of want to also note b can never be 0. Okay? So if you just think of it as numerator and denominator, the top is 0, makes the whole thing 0. The bottom is 0, makes the whole thing undefined. Okay? So you've got to be careful there. You can get your wires crossed very easily. Okay, so let's take a look at these fractions and see where we can apply this idea of the x-intercept means make y equal to 0, and the y-intercept means x equals 0, And if we've got something that's equal to 0 here that's a fraction, it means that the numerator has to be 0. Let's try and put all that together here. Okay, so if you have in this first one where we look and say the x-intercept means y equals 0, well, y is the output of a function, so that would be f at x. So I will make f at x equal to 0 and rewrite the function. And again, you have a fraction that's equal to 0, means the numerator is equal to 0. Who cares about the denominator? So you see that you really just have x plus 4 equals 0, so x equals negative 4. Okay? So now, if I want to look at the y-intercept, it would mean that x equals 0. And x is the input, so I'd be plugging that in. So I'd be doing f at 0 here, using the notation given to me in the function. 4 plus 0 over 0 is 4 over 0, which is undefined. So, interestingly enough, this function has no y-intercept. Okay? So, taking a look at the next example, if you see, when we say x-intercept, we know y equals 0, so I'll make y equal to 0, and I'll get a big ugly fraction that is equal to 0. And just a basic third grade rule again, you say that the fraction's equal to 0 when the numerator is equal to 0. Well, a little complex here because you got 2 equals 0, and that's going to happen never. Well, that just simply means that there is no x-intercept here. Okay? Now, this will come up in the idea of asymptotes, and you'll probably, if you already have seen it, can sort of imagine where these ideas of no x-intercept and no y-intercept are going. It has to do with the fact that these functions have an asymptotic nature to it, and I'll talk about that in a different video. So for here, in this middle function, we're going to look at the y-intercept, which means x is 0, and that's going to give me 2 over 0 to the 4th minus 0 plus 1, which is equal to 2 over 1, which is equal to y equals 2, and that is the y-intercept. Okay, again, it would be 0, comma 2 if you want to say it as an ordered pair, or it crosses the x-axis, y-axis, excuse me, at 2. Okay, so this last one's a little more straightforward because it'll have an x-intercept and a y-intercept. The x-intercept means y equals 0, so that's the output of the function, so I'll set m at x equal to it. And again, a fraction equal to 0 means that you can only have the numerator be equal to 0. So when is x minus 3 equal to 0? It's when x equals 3. And to do the y-intercept, you're saying x is 0, so I'm doing m at 0 using that notation, and getting 0 minus 3 on top over 0 plus 1 on bottom is negative 1 over 3 is negative 3. Okay? So, again, x-intercept, y equals 0, y-intercept, x equals 0, but applied here to this idea of rational functions. So you have to think, how do fractions equal 0? And you're still, if they say x equals 0, you're plugging 0 in for the right letter, and just, trying to apply some skills that you really should be ready to do, even if you haven't done them before. Okay? So let's take a look at it graphically here and see if it'll get to make sense, because we're talking about x-intercepts and y-intercepts. I did these from a mechanical standpoint, but let's look at some examples where there's some graphs. Okay, so here, in f at x equals 2x plus 6 over x minus 4, if I do the x-intercept, okay, that means where's y equal to 0? Doesn't matter which one you do first either, really. Okay, so you just have to have that kind of like crisscross reaction of x-intercept means y 0, y-intercept means x is 0. So I set the function equal to 0, again, because y is the output. I'm not putting it in for x because it says y is 0. So I know that that is going to create, excuse me, x minus 4, create an output of 0. So when is a fraction equal to 0? Well, when the top is. So you get 0 equals 2x plus 6, negative 6 equals 2x, and x equals negative 3. That is going to be the x-intercept. So I can actually go here and go to negative 3 on the x-axis and put a dot. Okay? Now I'm going to do the y-intercept. So the y-intercept And sometimes easier to do than the x-intercept because you see with the x-intercept you're kind of working backwards. But y-intercept when x equals 0, pretty easy to plug in 0. Okay, so we'll do f at 0. We get 2x, excuse me, we get f at 0 equals 2 times 0 plus 6 over 0 minus 4. Again, just plugging in the original function is going to give me 6 over negative 4, which is negative 1.5. Okay, so that is going to give me a point right here. Okay, so just a little smartboard magic here, not too impressive, but as I fade this out, you're going to see the graph behind it. That's the rest of the graph. So those points are absolutely right where they need to be. Hip, hip, hooray, right? Okay, so let's take a look at one more example. Just in this example, I want you to note a couple things that are coming up. There's this discontinuity line here that's an asymptote, okay? And there's actually another one over here, okay, at y equals 2, called an asymptote, where these functions will never touch. If you have some sense of them already, that's great, okay? You'll need to be aware of them quite well in the very near future if you haven't been made so already, okay? So what are we looking at now? A little more complex function. Okay, y equals x squared minus 9 over x plus 2. And if I want to do the x-intercept, it means y equals 0. So I'll set the output equal to 0, x squared minus 9 over x plus 2. Again, can't say it enough. When's the fraction equal to 0? When the numerator is equal to 0. And you're sitting there going, it looks like you're just crossing out the bottom. Well, yeah, I don't care what the bottom's ever going to be. Whatever x is going to be, it doesn't matter for the bottom. It only matters for the top in terms of making it 0. So we're going to find out when that is. And we notice something interesting here, that this is going to be x squared equals 9, right? So x equals plus or minus 3. Ooh, fun. So we've got two x-intercepts. Again, they're the values that when you plug them in for x, the whole fraction is going to be 0. Okay? So now when we go to the y-intercept, it means that x equals 0. So I'm just doing f at 0, if that's the notation. Just plug in 0, right? So you got y equals 0 squared minus 9 over 0 plus 2, which is going to give me negative 9 over 2, which is negative 4.5. I guess I'll be right about here. Okay? Now I'll know if I did this right, if I fade out the front graph into the back, and you'll see the complexity of the rest of the graph come to be, but we hit those points right on the money. Okay? So, and we see here that there also is this idea, this asymptote going on, which is a very popular thing in rational functions. Not one horizontally. Okay, there's actually one here on a slant that you'll talk about later. Okay, but this is it in a nutshell, guys. It really is. Again, the idea of y-intercept making x equal to 0 to find it, x-intercept making y equals 0 to find it. And then just applying that to the idea of these big, ugly fractions. And that major key idea here is if a fraction is equal to 0, which you're doing when you set the output equal to 0, it means the numerator is 0. If you're still not sure and you still want to get it right, it means you can cross out the denominator and still just solve the top part of the equation. Okay, I hope that's been a help, and feel free to practice, pass it on, do your best.